Welcome to the Explainer. Okay, think about the power that's charging your phone right now, or the engine that moves a giant cargo ship across the ocean, or even the roar of a jet engine. At the very heart of all of that, there's a single, fundamental piece of tech that has been shaping our world for centuries, and that's the heat engine. Today, we're going to dig into how it all works.
So take a look at this. This is a steam turbine, and it is absolutely massive. Machines just like this, spinning away inside power plants, are the reason your lights switch on. But how does this incredible thing actually work? What's the secret sauce for turning simple heat into motion and then into electricity?
Well, it all starts with a beautifully simple and seriously powerful idea.
When you boil it all down, this is what a heat engine does. It's any device that can take thermal energy, the heat from burning fuel or something similar, and transform it into mechanical output, into useful, powerful movement.
What's really cool is that pretty much every heat engine you'll ever come across can be sorted into two basic categories. And the entire difference, it just boils down to one simple question.
And that one crucial question is this: where does the combustion happen? Is the fire that's generating all that heat burning inside the engine itself? Or is it happening somewhere else entirely, with the heat being piped in?
And just like that single difference creates the two major families of heat engines that we see everywhere around us: external combustion and internal combustion.
Okay, so let's dive into this first type, where the heat source is actually kept separate from all the parts that are doing the moving.
Remember that giant steam turbine we saw a second ago? Well, that's the classic example of external combustion. You've got a fire, usually in a huge furnace, and it's heating water in a boiler. It turns it into incredibly high-pressure steam. That steam is then shot out like a focused jet, blasting against a whole series of blades and forcing them to spin like crazy. It's kind of like a pinwheel, but, powered by the world's most powerful kettle. But what happens when you bring that fire directly inside the engine? Well, you get a completely different, but just as powerful, kind of machine.
See, with an internal combustion engine, you basically get rid of the middleman. There's no boiler, no steam. The actual explosion, the expansion of those super hot gases from the fire itself, directly applies force to the engine's moving parts. It's a much more immediate way to get power.
And we can see two totally different but brilliant ways of using this internal power in action. You've got the continuous flow of a gas turbine, and then you have the rhythmic punch of a diesel piston engine. So first up is the gas turbine. This is the powerhouse behind jet engines and a lot of power plants. It all works in this smooth, continuous cycle. First, it sucks in and squeezes a whole bunch of air. Then, it mixes in fuel and lights it all up in the combustion stage, which creates this torrent of hot, high-pressure gas. And finally, that gas blasts through the turbine section, spinning the blades to generate power.
And you can see that whole process right here. Air gets pulled in on the left, it's compressed, ignited there in the middle, and then the hot gas blasts through the turbine blades on the right, making everything spin before it shoots out as exhaust.
Okay, so you've got that smooth, continuous flow of the gas turbine. Now let's switch gears completely and contrast that with a different kind of internal combustion engine. This one relies on distinct, powerful pulses, and you've definitely heard it sound in trucks and trains and ships. We're talking about the diesel engine.
So what's the big secret to a diesel engine? Well, it all comes down to this number, a ridiculously high compression ratio. We're talking about a piston squeezing a volume of air down to as little as 1/15 of its original size.
If you've ever used a bicycle pump and felt it get warm, you've felt the basic principle. Now just imagine that on an absolutely massive scale. When you squeeze air that much, it gets incredibly hot. I mean, so hot that when a fine mist of diesel fuel gets sprayed into that chamber, it just instantly ignites all by itself. No spark plug necessary.
So, the real takeaway here is that in a diesel engine, the compression is the ignition. The intense heat from the pressure alone is what kicks off the power stroke, and that's why they're sometimes called compression ignition engines.
All right, so we've covered a lot of ground. Let's just take a second and bring it all together and really nail down what we've learned.
At the end of the day, it really all boils down to this. Is the fire heating up a separate fluid, like water turning into steam, to do the work? Or is the hot, expanding gas from the fire itself doing the pushing directly? That's it. That's the fundamental split. From the steam turbines powering our grid to the diesel engines in our trucks, these two principles are just everywhere. They are, without a doubt, the engines that built the world we live in today. Which, of course, leaves us with a pretty big final question to think about.
What kind of engine is going to build the next one?